Today on How It's Made. Steel safes, false teeth, airplanes, and maple syrup. The first bank safes were made of wood reinforced with sheet iron. Thieves would just smash them open. Then came safes made of solid iron. Thieves would just blow them up. But then, to the crooks' dismay, came safes made of steel. It all starts with sheets of solid steel up to 3.5 centimeters thick and an automated machine with an oxygen and gas-fueled flame. The flame slowly cuts the plates that will form the walls of the safe. The cutting creates gases that are doused with water. A welder with a manual version of the same flame frees up the plates with a few last cuts. Then, using a large magnet, they stack the plates. Each one is labeled so the workers will know in what order to assemble them. They're assembled by a welder who uses a semi-automatic soldering gun. The solder is a special welding wire made of several different metals. It rolls off a spool as needed. Elsewhere in the factory, a semi-automatic saw cuts flat bars of steel. These bars will form the frame that'll surround the steel plates. Meanwhile, another machine, called a turret, fashions steel bars into moving parts for the locking mechanism, and also into hinges. That milky liquid is a lubricant. Normally, you see raw material move on an assembly line from tool to tool. This is just the opposite. The steel bar stays on the turret from start to finish. The tools come and go. Workers take pieces of sheet metal cut into shapes by laser and bend them in a press to make various parts and mechanisms. Meanwhile, the large steel plates they cut earlier go into a hydraulic press to make them perfectly flat. It's finally time to put all the components together. They construct the frame in an assembly jig, then insert the plates for the sides, top, and bottom. Using the semi-automatic soldering gun again, they fuse the pieces together. They measure the angles, then use a giant clamp to square the safe. Finally, they install the plate for the back of the safe and solder the joints. They stand the safe upright and grind down the soldering lines until they're smooth. This factory also produces what's called a composite safe, made of soft materials such as copper, aluminum, and low-grade steel. But it has a cement core, making this safe harder to break into. The finished safe gets 3 coats of paint. Then in the finishing department, they install the mechanical or electronic locks and locking mechanisms, as well as the internal time lock mechanism. The time lock allows access to the safe only at certain times of day, such as the bank's business hours. Even if someone picks the outside combination locks, the door won't open outside those set hours. The machines that sterilize medical instruments use ethylene oxide, a highly toxic gas. Now, there's a new method that's safer, more effective, and less expensive. This new machine uses ozone as the sterilizing agent. Ozone is a form of oxygen. Until the 1800s, false teeth were made of animal bone, ivory, or actual human teeth. They came from poor people who sold their teeth and from dead bodies. Today's dentures are usually ceramic. They start by heating a sheet of wax over a flame. They press it onto a rough plaster model of the patient's mouth sent in by the dentist. The lab technicians use this model to prepare what's called an impression tray, what the dentist will use to make a rubber mold to cast the dentures. They apply an acrylic material over the wax lining, forming a handle so they'll be able to remove it afterwards. Once the acrylic hardens, they pull it out of the model and discard the wax. The dentist fills this new acrylic tray with rubber to take a final impression. The lab uses the hardened rubber as a negative mold of the patient's mouth. They fill it with plaster to make a new, more precise plaster model. Then they use the new model to make the part of the dentures that fits on top of the patient's gums. They take special orthodontic acrylic and press it into the model to form what's called the base plate. Then they heat a sheet of wax to form a rim on the base. This new acrylic and wax model now goes back for another fitting in the patient's mouth. The dentist takes a series of measurements to show the lab exactly where to place the teeth. The model goes back to the lab, where technicians select the teeth that'll best suit the size of the patient's mouth. They install the teeth one by one into the model's wax rim. Then they send the model back to the dentist for the final fitting. The dentist checks that everything is centered and that the patient's bite is properly aligned. If the model fits well and looks good, the lab can finally begin to manufacture the dentures. They position the model in a special holder called a flask, then attach channels through which acrylic will later be injected. This acrylic will replace the wax holding the teeth in place. But first, to get rid of the wax, they have to cast a plaster mold to hold the teeth in place. Once the plaster dries, they submerge it in hot water for 5 minutes to melt the wax inside. They rinse the plaster mold with warm water to remove any wax residues. Then they apply what's called a separator, a chemical that will keep the acrylic from sticking to the plaster mold, just like greasing the pan when you're baking. They position a cylinder of acrylic right over the flask. Using an air pressure piston, they force the acrylic into the plaster mold. They submerge the mold in boiling water for 35 minutes to harden the acrylic. Once the flask has cooled down, they break the plaster. The false teeth are now securely rooted in acrylic gums. A bit of finishing and they'll be done. An ultrasonic bath gets rid of any remaining plaster. They polish the acrylic with pumice, then shine it up with a polishing compound. The set of false teeth is finally ready. When a patient doesn't need a full set of dentures, just a few teeth, they get what's called a partial, made much the same way, but hooked on at either end to the patient's natural teeth. Aviation was once the exclusive domain of commercial and military pilots. Not anymore. Today, many amateurs get their pilot's license and take to the skies in light aircraft. Not for a job, but for the sheer pleasure of flying. To construct the body of these light aircraft, they start with two types of cloth. One woven from glass fibers, fiberglass, the other from carbon fibers. Carbon is a chemical element that's stronger than steel. Both materials go through a laminating machine that coats them with an epoxy resin. To begin forming the various parts that make up the body, workers lay strips of the laminated fabric into molds. The engineering plans dictate the precise positioning of the strips, which is critical for strength and durability. They lay in carbon fiber cloth where they need to have extra strength without additional weight. Areas such as this, the passenger compartment of the cockpit. To make the fuselage, they sandwich a foam core about 10 millimeters thick between two layers of the fiberglass cloth. The foam also insulates against heat, cold, and noise. Workers coat the edges and joints with resin, filling any voids. Once all the fabric is in the mold, it's time to vacuum bag it. First, they cover everything with a layer of perforated plastic. Then with a breather cloth, which looks like a white wool blanket. Then comes another layer of plastic. They attach a vacuum to suck out all the air. The excess resin exits through the tiny holes in the plastic and soaks into the breather cloth. Now that the mold is airtight, it can begin to cure. They put it into an oven at 40 degrees Celsius for 8 hours. Once the molds come out of the oven, workers install the internal structure. Then, using the same epoxy resin they used earlier to laminate the fiberglass and carbon fiber fabrics, they bond the tail's upper and lower shells together. They do the same with the wings. The parts are left to cure overnight. The next day, they finally come out of the molds. Next stop, the trim shop. Workers remove the excess fiberglass and cut out the windows. The parts go back for a final curing. The oven is 80 degrees Celsius, twice as hot as last time. 18 hours later, out they come for painting. Workers sand the parts and coat them with an epoxy primer first. The finish coat is a polyurethane which resists weathering. Meanwhile, other workers assemble and test various components, such as the electrical system. A computer guides a machine to cut all the metal parts, such as the instrument panel. The cutting machine doesn't have a blade, but rather a sand and water jet that's powerful enough to cut through metal. A certified aircraft welder prepares the engine mount, the base that will hold the engine in place. It's made of high-grade carbon steel. At the final assembly stage, workers install the engine and other previously assembled components into the fuselage. Workers position the wiring and plumbing, then hook them up. They screw on the wingtips, which already have their navigational lights. An avionics technician powers up the airplane for the first time to function test everything. The final inspection takes place where it really counts, in flight. How do maple trees make sap? They accumulate starch during their growing season. With the spring thaw, enzymes transform the starch into sugar. When the trees absorb water through their roots, it mixes with that sugar to make sap. Long before the white man came to North America, the native Indians revered the maple tree. In early spring, they'd pierce its trunk with a tomahawk, then place a wood chip under the hole to channel the sap into a bark container. Then they boiled the sap over a fire in clay pots. The Indians introduced maple syrup to the European settlers. Today, most producers use tubing instead of sap buckets. No more trudging through the snow from tree to tree. The time to collect sap is in the early spring, when the maple trees are still dormant and when the temperature hits 3 or 4 degrees above freezing. The freeze and thaw cycle alters the pressure inside the tree and starts the sap flowing. The first step is to tap the trees. They drill a hole 1 centimeter in diameter, 5 centimeters deep. Then gently insert a spout made of metal or plastic. It's important not to damage the bark. That not only harms the tree, but also lets air in the sap, which ruins the flavor. You don't see too many sap buckets around anymore. Today, sap is pumped through polyethylene tubes to larger collector tubes. Then into the pumping station. Sap is 97.5% water and only 2.5% sugar, so to transform the sap to syrup, they have to boil it down. It takes 40 liters of sap to make just 1 liter of syrup. When the tank fills up, the sap is automatically pumped to the sugar house into a stainless steel tank. The more advanced producers use a specialized machine that partially concentrates the sap by reverse osmosis. This more than triples the sap's natural sugar level and means they'll have less boiling to do. From there, the sap flows to the evaporator. They heat the sap to the boiling point and keep it boiling however long it takes to evaporate 66% of the water. If the water evaporates too slowly or too quickly, that'll adversely affect the color, flavor, and texture of the syrup. However, and here's where expertise is everything, there's no set cooking time. Experienced maple sugar producers can tell when it's ready just by looking at it. They test the sugar level using a device called a hydrotherm. When the syrup is just right, they run it through a pressure filter to remove calcium residues and other impurities. They store the syrup in steam-cleaned barrels. The lab at the central warehouse tests a sample from each drum. Using sophisticated instruments, technicians classify the color from dark to extra light. They also assess the quality. Lower grade syrup is for industrial use, higher grade for the retail market. They pasteurize this syrup, then put it into huge stainless steel storage tanks. The tanks are vacuum sealed with a nitrogen barrier to preserve the flavor and color and to prevent fermentation. It also keeps the syrup from crystallizing. The lab then uses an instrument called an atomic absorption spectrophotometer to analyze the syrup's mineral content, making sure it meets market standards. Next, they warm the syrup in stainless steel heaters and run it through industrial-size filters. This step ensures the syrup will be perfectly clear. Then, just before bottling, they heat the syrup again, this time to 82 degrees Celsius. This not only sterilizes the bottles, but also guarantees the syrup will have a 4-year shelf life. Maple syrup is high in sugar but has somewhat fewer calories than honey or brown sugar. It's 100% pure and natural, and it's a good source of 3 essential nutrients: calcium, potassium, and magnesium. If you have any comments about the show, or if today on How It's Made, plastic injection molds. We'll watch them take shape. Automotive oil filters. We'll have all the dirt. Filing cabinets. You can file this one under F for fascinating. And blown glass. We promise you full transparency in this report. If you take a close look at the products around you, you'll notice that many are made of parts that have been assembled together. One way factories make product parts is by melting materials such as metal, rubber, or plastic, then pouring or injecting them into molds. To make a plastic part for a product, the manufacturer has to first commission a mold-making company to design and produce a plastic injection mold. The mold begins as bars of chromium steel, a high-durability metal that can withstand repeated high-pressure injection of plastic. Workers assemble several bars into a block called a mold base. They mount this base on a milling machine, which shaves the bars to the right dimension. This step is critical, enabling them to later machine the base into a mold that's faithful to the technical design, right down to the 100th of a millimeter. A mold usually consists of 2 halves, each of which is comprised of several components. The factory drills strategically positioned holes in the bases for the guide pins and bushings that hold the components together when the plastic's injected. A grinder now goes to work smoothing and leveling all surfaces. This prepares the base for the high-precision machining operations that will transform it into a mold component. A computer-guided tooling machine called the CNC slowly machines the base, wearing away the steel particle by particle to create the mold component's shape. This one, part of a mold for the plastic rim around a snowmobile's front headlight, takes 20 hours to complete. From here, most mold components go on to a second tooling machine, especially if they have some fine detailing that this CNC machine is incapable of carving. The second machine is outfitted with a copper electrode in the shape of the plastic part, in this case a snowmobile oil gauge. After polishing the electrode to ensure flawless casting, they use a sophisticated measuring device to verify the dimensions. The electrode goes face down on the second tooling machine called the EDM. Directly underneath is the mold half that's already been partially formed on the first machine. A strong electric current runs through the electrode and penetrates the mold, forming a cavity in the shape of the electrode. After tooling, they drill coolant lines. This is for the cooling fluid they'll use to accelerate the hardening of the molten plastic. Some plastic product parts, like that snowmobile oil gauge we saw earlier, have lettering on them. The factory engraves the letters in reverse inside the mold cavity. After the plastic's injected, the writing comes out frontward and raised. The surface of the mold cavity is pretty rough from all that tooling, so they polish it smooth to ensure a proper casting. Here's what the 2 halves of a finished mold look like. The pins and bushings fit together to close the mold before injecting the hot liquid plastic. Once the plastic cools and hardens, it's just a matter of extracting the molded plastic part. Here's a different molding method. A two-step process they're using to make these buttons that go on the steering handle of a jet ski. First, they mold a structural base out of hard white plastic. Then they put the base into a second mold and inject a rubber-like gray plastic. This softer plastic covers everything but the raised lettering, giving the button a softer feel. Factories also make molds for aluminum injection and rubber injection, among other materials. They build those molds from different types of metal, but using the same techniques. Changing your car's oil filter a couple of times a year is an easy way to prolong the life of your engine. The oil pump forces oil through the filter to the moving parts in the engine. The filter's job is to block dirt and metal debris from getting in between those parts and causing engine damage. They make many oil filter parts from steel coil, a sheet of steel on a roll. They start by unwinding the roll and feeding the coil into a press. The press contains a series of dies, each of which progressively stamps the steel into the shape of the specific part they're making. This press is churning out tapping plates, part of the component on the end of the oil filter that screws onto the car's engine. Hot off the press, the tapping plates travel on a magnetic conveyor to the welding station. There, a robotic arm loads them onto the welding carousel. But before any welding begins, a nozzle applies sealant around the rim of each plate. This is to fill any gaps left between the parts after welding. A robot now welds the tapping plate to another steel part called the bottom ring. This ring will hold the gasket, the rubber seal that prevents oil from leaking out as it travels through the filter into the engine. The welded parts, known as the bottom assembly, now go onto a machine that cuts a thread pattern through the center. This will enable the oil filter to be screwed onto the engine. Another press, meanwhile, produces the oil filter's steel body, called the canister. The dies first stamp out a rough canister shape. Then they reduce the diameter and make the can taller. Then they cut off the excess. Elsewhere in the factory, another machine cuts and perforates pieces of tin-plated steel coil and rolls them into tubes. We'll see where those tubes go shortly. Yet another machine prepares the filter's key component, a filter paper that works like a fine sieve, trapping dirt, carbon, and soot. First, the machine pleats the paper so that it'll fit inside the canister. Next, the machine cuts the continuous ribbon of pleated paper into lengths. Then it folds each piece into a circle, fastening the ends with a steel clip. The next machine assembles what's called the filter cartridge. It places each filter paper over a tube. The tube's job is to reinforce the paper against the force of the oil pumping through it. The next machine glues a capping disc on each end of the filter paper to hold the tube in place. A heater cures the glue. Now for the final assembly. As the canisters go by upside down, automated arms insert the filter cartridges. A worker then puts a thin rubber disc on top of each cartridge. This disc will prevent the oil from draining out of the filter. Now for those bottom assemblies we saw them making earlier. A worker positions one on each canister. Then a machine called a seamer folds its edge down, forming a rim, just like the rim of a soup can. Now the conveyor turns the filters right side up as they file by 5 nozzles spraying powder paint. An infrared oven dries the paint in about 90 seconds. Then a printing machine stamps on the product information. The conveyor now turns the filters upside down again as they travel to the gasket inserter. Its automated plungers insert a gasket into each bottom ring. These automotive oil filters are finally finished and ready to do the dirty work. Whether you work in a sprawling corporate office or in a home office, filing cabinets are an essential component of an efficient workplace. They keep your paperwork tidy, organized, and out of sight, yet just a drawer away. And when you're short on space, they make a nifty counter for the coffee maker. Filing cabinets begin as sheets of cold roll steel, a thin type of metal that's easy to bend, weld, and paint. As the sheet comes off the roll, it goes through a straightening machine that removes the curve. Then into a press whose dies punch out the shape of the specific part, complete with holes, slots, and embossments. A filing cabinet is made up of 60-plus steel parts. For the top-selling models, the factory has dies specially designed to punch out each part. But that's too costly a system for models that aren't mass-produced. So to make low-volume or custom-made filing cabinets, the factory uses this computer-controlled punching machine. This equipment operates at a far slower speed than the presses we just saw, but the advantage is that it can be programmed to punch out any size, shape, or design, no matter how complex. Several filing cabinet parts are designed to be bent into shape. Workers do that manually, using a machine called a press brake. This particular part will become the top of the filing cabinet, so they're making downward folds along the perimeter to create 3.75 centimeter wide edges with strong and tight corner seams. This machine is called a dedicated bender because it's used to bend one type of part only, the filing cabinet doors. The factory produces doors in such volume that it pays to design a special machine to shape them. The doors, too, are bent downward along the perimeter to create edges 1 centimeter wide with tight corner seams. The cabinet's base is welded from the same type of steel sheeting as the other parts. Small steel reinforcements make it rigid enough to support the excessive weight of file-filled drawers. To join the cabinet's sides and back, robots perform what's called resistance welding, fusing metal using heat from an electric current. The next set of robots welds that side and back unit to the cabinet top. After this, workers attach the base using what's called MIG welding, welding that adds extra metal along the joint to create a strong seam. Once again, it doesn't pay to invest in robotic welding equipment for models that aren't mass-produced, so they manually weld low-volume items such as those small filing cabinets that roll under desks. In the paint department, rotary atomizers envelop the filing cabinets in a mist of paint that contains a synthetic resin for durability. These atomizers lace the paint particles with a negative electric charge. This draws the particles to a positive charge on the cabinets, creating a thorough and even coat. After 20 minutes in an oven to bake the paint, assembly can begin. Ball-bearing sliders on which the drawers will sit, tracks for the fold-down doors, and door stops so the doors can't be pulled off their tracks. There's also a locking system that simultaneously bolts both sides of each door, rendering the files inside inaccessible. The last step is to install the doors and drawers using a rubber mallet so as not to damage the finish. Each drawer can support up to 90 kilograms of files. An interlock system lets you open only one drawer at a time. This prevents the cabinet from toppling forward. A glass blower can transform a sizzling blob of molten glass into sheer sculpture, an object that's functional or decorative or both. Blown glass can be on the cutting edge of modern design, quite a feat for an art that's more than 2,000 years old. The first hollow glass objects date back to 1500 BC. The invention of the blowpipe around 30 BC revolutionized the craft. Until then, objects were either carved from solid glass blocks or molded from molten glass. The blowpipe enabled glassmakers to expand and shape glass, and it made fast, inexpensive production possible. This meant that everyday items, not just luxuries, could now be made of glass, accessible not just to the rich, but to ordinary people too. When you see these spectacular shapes and colors, it's hard to believe that blown glass comes from this bland, lumpy stuff. This is silica, a natural material derived from sand, mixed with thinners and stabilizers such as potassium and limestone. The glass blower recycles any leftover colorless glass, then loads the mix into the melting furnace. After 12 hours at fusion temperature, 1200 degrees Celsius, the raw material transforms into colorless liquid glass. The glass blower uses a blowpipe, a long steel tube with a ring or pear-shaped end, to collect what's called a gather, a glob of this red-hot molten material. To color the gather, she quickly rolls it in finely ground colored glass. At this stage, the glass is honey-like in consistency, though it's cooling and thickening by the second. She fuses the color layer by reheating the glass for a few seconds in a smaller furnace called a glory hole. Next, she rolls the glass against a ladle-shaped block to form a starting shape for blowing. A gentle blow or two bulges it into a hollow bubble. By now, the cooling glass has thickened to the consistency of caramel, making it more controllable and shapeable. The glass blower stretches and shapes the glass with different blocks and hand tools. The glass is like hardened caramel now and holds its final shape. She scores the glass where it meets the blowpipe, then cools it further with compressed air. On the opposite end of the glass, with a bit of hot glass, she attaches a solid metal maneuvering rod called a pontil. Then she applies a single drop of cold water on the score line to crack and break the glass off the blowpipe. Using another pontil, she plugs the resulting hole with hot glass. Then it's back to the melting furnace to attach a gather. It's critical to always rotate the glass so that it doesn't droop and become lopsided. The glass blower shapes this gather not with a block, but by hand. She protects herself from the intense heat by using a thick stack of soggy newspapers. Using an ordinary pair of scissors, She forms ridges. Then she twists the ridges to spiral them. She cools and hardens the finished design using compressed air. Then it's a quick blast in the glory hole to equalize the temperature throughout the piece. This blown glass lemon reamer has taken all of 8 minutes to make. Now it goes into an electric kiln for a slow 12-hour cool down to prevent cracking. Meanwhile, the glass blower starts a new piece, a large vase. More blowing, more shaping. Then, while her co-worker blows air to further expand the glass and thin it out, she cools the vase's bottom with wet newspapers. This holds the cutoff point at the top. After reheating the glass to re-soften it, they stretch it, lengthening the vase. Once they finalize the shape, they use a wooden paddle to flatten the base. Now for some eye-catching decoration. Vivid colored glass coiled like taffy over the entire vase. Certain designs require cutting off a portion of the finished piece. That leaves a rough, opaque edge they must extensively grind and polish. A lemon reamer, a vase, even a mortar and pestle. A glass blower's work is clearly remarkable.